In section 6.1, we looked at how to solve systems of equations using graphing. And in that section, I told you that there would be two other more reliable methods in how to solve systems of equations. So in section 6.2, this is where we'll get our first look at the first method outside of graphing, which we will call the substitution method. And if you think about what substitution means, it means that you would take something that you know a variable is equal to and plug it in for that variable in something else. That's exactly what the substitution method asks you to do when it comes to systems of equations. So in example number 1, it says solve the system of equations by substitution. So notice it says x equals 2 and x plus 2y equals negative 16. We know that x is equal to 2. So what I'm going to do is take the fact that x equals 2 and I'm going to plug it in for the x in the other equation. So I would have 2 plus 2y equals negative 16. Now I'll just solve for y. So I'm going to subtract 2 from both sides and have 2y equals negative 18. Divide both sides by 2, so I get y equals negative 9. Now thinking back to when we were solving systems of equations by graphing, our answer was where the two lines intersected. So we're still going to answer the problems as if we are still graphing it. So since x equals 2 and y equals negative 9, I'm going to write my answer as an ordered pair to negative 9. So again, I'm going to write my answer as if I still graphed it by showing an ordered pair for the place where the two lines are intersecting. And again, what this means is if I were to plug 2 in for x and negative 9 in for y into our original equations, this point is shared by the two lines, so it would work in both equations. It would give you true statements. Let's move on to example number 2. Again, we're going to solve the system of equations by substitution. And what you're going to see here is the problems are going to get progressively harder. So in the last problem, it said x equals 2. This time it says x equals 2 plus 4y and x plus 2y equals negative 16. So now this time we still know that x is equal to something. So we're going to take what x is equal to and we're still going to plug it in for the x in the other equation. So I'm going to take that x out and put 2 plus 4y in for that x, and I still have the plus 2y equals negative 16. That was the rest of the equation. So again, I took this x out, replaced it with what we knew x was equal to. So here's the x. So x plus 2y equals negative 16. And notice now we have the same variable in the equation. We don't have two different variables. So that's kind of a checkpoint that you can use. Does this still say x plus 2y equals negative 16? It does, except we just replace the x with what we knew x was equal to. And the second checkpoint would be to make sure that you have the same variable in your new equation, which we do. We don't have an x and a y this time, we only have a y. So now that we only have y's, we can solve for y. So the first thing I would do is combine like terms. So 4y plus 2y is 6y. Then I would subtract 2 from both sides. So I'd have 6y equals negative 18, divide both sides by 6, and y equals negative 3. But remember, I'm going to answer my problem as if I graphed it. And so far I only know that the y value is negative 3. But I do know that x is equal to 2 plus 4y. So now that I know that y is equal to negative 3, I'm going to take that negative 3, and I'm going to plug it back in up here and solve for x. So I have x equals 2 plus 4 times negative 3. And remember, I got to follow the order of operations. I'm going to multiply before I add. So I have x equals 2 minus 12. So x equals negative 10. So my final answer would be negative 10, negative 3, meaning if I were to actually graph these two equations, they would intersect at negative 10, negative 3. And I can always check my answer by putting the negative 10 in for x and the negative 3 in for y and making sure it worked out in both equations. Here's example number 3. Solve the system of equations by substitution. So this time we have 10x plus 2y equals 10 and y equals 3x minus 3. So notice this time we have the y by itself. This time we know y is equal to 3x minus 3. So I'm still going to take the fact that y equals 3x minus 3, but I'm going to substitute it into the first equation for the y. Notice it's 2 times y. So when I substitute 3x minus 3 in for that y, I need to make sure that I put the 2 in front of it. So anytime you substitute, it's best if you put parentheses around it when there is a coefficient you're going to be multiplying by. So I have 2 times 3x minus 3 equals 10. So again, what's the point of these parentheses? It's the fact that I have to take 2 times that entire y value in order to solve this problem. So again, our checkpoint, does this still say 10x plus 2y equals 10, just like it did originally? Yes, except I just replaced the y with what it's equal to. And the second checkpoint would be that we now only have x's in our equation. So now we're ready to solve. So let's distribute first. 10x plus 6x minus 6 equals 10. Combine like terms. Then I would just add 6 to both sides. So now I have 16x equals 16. Divide both sides by 16, and I get x equals 1. But remember, I'm going to answer this as if I graphed it. So far, I only know that I have an x value of 1. I don't know what the y value is. But remember, I know that y is equal to something about x. So now that I know that x equals 1, I'm going to take the fact that x equals 1 and substitute it back into our y equals equation. So I have y equals 3 times 1 minus 3. Again, remember to use the order of operations. So 3 times 1 is 3, and 3 minus 3 is 0. So my answer would be 1, 0. Always remember to answer as if you graphed it. So again, this means that if I were to take these two equations, get the y by themselves, do the m and the b, slope, y-intercept, that the two lines would intersect at 1, 0. And again, these problems are getting progressively harder. So especially in this problem, we have example number 4, solve the system of equations by substitution. So this time we have 4y minus x equals 4 and y plus x equals 6. And the last examples, we always started off with a variable already by itself. If you notice, none of the variables are by themselves originally from the start in this problem. So our first step in substitution, if there isn't already one by itself, is to get a variable by itself. So just to reiterate, if there isn't already a variable by itself, the first step in substitution is to get a variable by itself. And always look for the variable that's going to be the easiest to get by itself. So always look for the variable that doesn't have a coefficient. In this case, we have a y and an x that doesn't have a number in front of it. I would probably not choose this x up here just because it's minus x. So if I were to get that x by itself, I'd have to subtract the 4y and divide by -1. I want to try to avoid that. So I'm going to look at this equation where the y and the x, neither of them have a coefficient. So you could solve for y or you could solve for x. It doesn't matter. So just say let's solve for y. So to get the y by itself in that second equation, I would subtract x from both sides. So I'd have y equals 6 minus x. I could have just as easily solved for x and subtracted the y and ended up with x equals 6 minus y. In that case, I would take what x is equal to and substitute in for the x in the other equation. But since I chose y, I'm going to substitute in for y. So now that I know that y is equal to 6 minus x, I'm going to take the 6 minus x and substitute it into the other equation. So I would have 4, since it's 4 times y, so 4 parentheses 6 minus x equals 4. If you had solved for x in this equation and you substituted that 6 minus y in for the x, you'd have to realize that there was a minus sign, so it'd have to be like minus parentheses 6 minus y. So that is actually probably a little more complicated, so it was a good call for us to solve for y to begin with. So again, our checkpoint. Does it still say 4y minus x equals 4 like it did originally? It does. And do I have all of the same variable? I do, so I'm ready to solve. So I'm going to distribute first. 4 times 6 is 24. 4 times negative x is negative 4x or minus 4x. And then minus x equals 4. Combine like terms. Negative 4x minus x would be negative 5x, since there's technically a negative 1 in front of that second x there. Then I would subtract 24. 4 minus 24 is negative 20. So I divide both sides by negative 5, and I get x equals 4. And again, I need the ordered pair where the two lines are intersecting. So now that I know that x equals 4, I'm going to take the x equals 4 and plug it back into one of these equations up here. We could plug it back into this equation. We could plug it back into the y plus x equals 6 equation, or I could even plug it into the y equals equation. To me, it makes the most sense to plug it into the y equals equation since I need to know what y is equal to. So I'm going to take that x equals 4 and plug it in right here. So I would have y equals 6 minus 4 and y equals 2. So again, finish my ordered pair. My final answer would be 4, 2. Always answer it as if you graphed it. So again, this means that if I were to get the y by themselves for both of those equations and then graph them, they would have intersected at 4, 2. This point is shared by these two lines, and also meaning that if I were to plug the x in for x and the y in for the y, it would work out in both equations. One more example, number 5. The instructions are still to solve the system of equations by substitution. And as you've seen, the problems got a little bit harder each time, and this one especially. Notice that there is not a variable by itself. And remember from the last slide, the first step in the substitution method is to get a variable by itself as if there isn't already one by itself. So notice we have 11x minus 7y equals negative 14 and x minus 2y equals negative 4. We do not have a variable by itself. However, I can easily get one by itself by getting this x by itself. I would not choose to get this x by itself since it has 11 in front of it. I would not choose to get this y by itself since it has a negative 7 in front of it. And I would not choose to get this y by itself because it has a negative 2 in front of it. In order to get this x by itself, all I'd have to do is subtract 2y over, and then the x would be by itself. So again, always choose the variable that's going to be the easiest to get by itself. So again, I'm going to choose to get that x by itself by adding 2y to both sides. So I would have x equals negative 4 plus 2y. If you wrote it as 2y minus 4, it's exactly the same thing. So now that I have x by itself, I'm going to take what x is equal to and substitute it in for the x in the other equation. Since it's 11 times x, make sure you put parentheses around what you're substituting in. So I have 11 times parentheses negative 4 plus 2y minus 7y equals negative 14. So again, here's our checkpoint. Does this still say 11x minus 7y equals negative 14 just like it did originally? It does. And do I have all the same variable now? I do. So I'm ready to solve. Distribute, so I end up with negative 44 plus 22y minus 7y equals negative 14. Combine like terms, so negative 44 plus 15y equals negative 14. Add 44 to both sides. So you end up with 15y equals 30. Divide both sides by 15, and you end up with y equals 2. So in my ordered pair so far, this is what I know. I still need to find x. So again, I have the option of substituting it back in for the 2 in for y in the first equation, the 2 in for the y in the second equation, or I can substitute the 2 in for the y in the x equals equation. To me, it makes sense to plug it back into the x equals equation since I need to know what x is equal to. So I'm going to again take the y equals 2 and plug it in right here. So I would have x equals negative 4 plus 2 times 2. Follow the order of operations, so negative 4 plus 4, so x equals 0. So again, if I were to graph these two equations, they would intersect at 0, 2. Basically, 0, 2 would be a y-intercept, so it's just telling me that these two equations have the same y-intercept. So that's it for this section. We'll do lots and lots of practice over this, and the next method, which is the elimination method from section 6.3, and just know that we're going to do lots and lots of examples of all types of methods so that we get really familiar with it before we move on and take a quiz or a test over it. As always, jot down anything you didn't understand that we can cover in class before we move on, and we'll see you then.